Hello, my name is Catalina Gonzalez Duenas. I'm a third-year PhD student working under the supervision of Dr. Paget at Rice University. My research focuses in the assessment of coastal structures under hurricane hazard while considering cascading effects and time-varying factors. And today I'm going to touch upon this last topic and discuss about methodology for the assessment of coastal structures under time-varying factors. An outline for my presentation is first I'm going to discuss about the background and the motivation of this study, followed by the general objective, the proposed framework, and its representation with a probabilistic graphical model. And then to showcase the framework, we're going to use a case study based on a residential coastal elevated structure. And then I'm going to finish with some conclusions and contributions of the work. So coastal communities face severe socioeconomic challenges posed by the disastrous impacts of natural hazards. These challenges are being exacerbated by factors such as changing climate, aging of existing infrastructure, the increase of population, and the rise in property value. We can see in this picture Hurricane Laura that made landfall on August 27 in southwestern Louisiana, and actually was the first Category 4 hurricane to ever make landfall in this region. So this poses a lot of questions on how are we designing our structures safe enough for the hazards that are coming in the future. To assess these, performance-based methodologies have been used to assess the performance of structural systems during a natural hazard event for design, retrofit, and risk assessment of structures. So it starts by defining some performance levels. There are qualitative measures of the performance of the structure, such as operational or flight safety, that are coupled with hazard events and structural parameters to compute the expected levels of damage of the system. This is coupled, the consequences that, that these damages lead will give us to some decisions. Common term that appears in performance-based methodologies is fragility, that will give us the probability of damage given some intensity measures, such as wave height or surge depth. Performance-based methodologies were originally proposed in the earthquake engineering community a couple of decades ago, and recently have been extended to other types of natural hazards, such as wind, hurricanes, and tsunami, which have posed key advancements in coastal engineering and the assessment of coastal structures by introducing concepts such as the interaction of the structure with the environment and the multi-hazard nature of coastal hazards, such as hurricanes. However, existing performance-based engineering frameworks are focused on punctuated hazards and do not consider time-varying factors, such as climate change and loss of performance over time. To address this, in this study, we developed a framework to assess the performance of coastal systems subjected to both chronic and punctuated natural hazards by incorporating time-varying factors. And as a case study, we will perform the assessment of a typical Gulf Coast elevated structure subjected to wave and surge loads while considering some time-varying factors. So first, the methodology starts with defining some performance objective. As I mentioned, these are qualitative measures of the performance of the structure, followed by the structural characterization that we define by the vector phi. These include the uncertainties in the material and geometrical properties of the system. Then is followed by the hazard analysis, where the vector lambda will define the intensity measures. These intensity measures can include the landfall of the hurricane, can include the surge depth, wave height, wind speed. Then with this hazard analysis and the structural characterization, we can follow by the interaction analysis that, depending on the system, on the structure and the analysis, can be fluid structural interaction, also the structural interaction. And then we perform the structural analysis where we define the vector theta that will basically define the response of the structure, that it's usually also named as engineering demand parameters. With these parameters, demand parameters, we can actually follow by the damage analysis of the system, where we define the vector delta that will tell us if the structure has surpassed certain levels of damage based on the demand and the resistance. Then we follow by the loss analysis that will actually leads us to the computation of the marginal probability density function of the decision variable. Is commonly named loss analysis because these decision variables are usually defined as economic losses or loss of life or downtime of structures or systems by the vector gamma of costs related to each damage state defined for the system. And then with these damages and the loss computed, we can make some decisions. Some of the factors that will affect these components over time might be the reuse of structures, such as a building that was designed as a residential building changing to a business, and not acceptable losses that are related with the loss analysis. So if the losses are too high, the stakeholders might want to change the performance objectives and actually the structural design as well. For the hazard analysis, we have factors such as climate change and variability of the hazards. For the structural parameters, we have aging and maintenance. Aging can change, for example, the stiffness of the structures over time. Then we have market changes. We have changes in land use and depreciation. We have also some factors affecting the decision process, such as risk aversion of the stakeholders making the decision and some sustainability requirements. This decision making will obviously change the performance objective and the structural parameters. So how do we account for all these dependencies between the random variables in the system when our objective is to compute the marginal density function of the decision variable, in this case loss? So one thing we can see is that by this actual flow of information, we can use these causal dependencies, and we do that using a probabilistic graphical model. In specific here, the Bayesian network. So a Bayesian network in general is a directed cyclic graphical model that represents the joint density function px of a set of random variables. So for example, in this toy network, we can see that the links represent the causal relationships and the nodes represent the random variables. So if we want to, the joint probability will be given by the product of the individual conditional probabilities, and if we want to compute the marginal probability of one of the random variables, for example x4, we will just have to integrate over the variables that is dependent. So another feature, and a very important feature of Bayesian networks, is that we can actually incorporate evidence over time. So, for example, if we have an evidence in the random variable x2 and we want to compute the marginal probability distribution of the variable x3, we can do it by calculating the probability of x3 given e. We propagate these uncertainties using a Bayes theory. So, as a case study, we're going to implement this framework on a typical Gulf Coast elevated coastal structure subjected to wave and surge load. This is the actual structure located in Galveston area. Here is Galveston Island, and just to give a little bit of context, here is the city of Houston. So first we start by the definition of the hazard, that is intensity measures. To consider factors that might affect hurricanes in the future, we consider the changes in the velocity of the forward speed and sea level rise. We do this through synthetic variations of storm FEMA 33, that is a synthetic storm that leads to search depth values related to 100-year return period. So we start with at CIRC+1 simulations for 3 years, 2030, 2050, and 2100. Although for representation purposes, we're just going to use the year 2050 for the results. Then for each year, we define 3 levels or RCP, that is the representative concentration path, that basically tells us the levels, the projected levels of carbon dioxide in the atmosphere in the future. Being 8.5, the scenario with highest concentration of carbon dioxide. Based on the work by Cobb et al., we use projections of sea level rise, and we define for each of the levels a normal distribution for the sea level rise. And then, based on the work by Yu and Irish, we define the forward velocity of the storms as an uniform distribution with representative values for the region that is between 3 and 12 meters per second. Then, for the structural analysis, the response and the damage components, we use a fragility model. So we use the fragility models proposed by Tomishek that correspond to Hurricane Ike in the Galveston region. And these parameterized fragility models are function of the significant wave height, the freeboard height, that is actually this height that free height without water, let's say, and the age of the structure. So based on this fragility function, we find the demand, let's say the intensity measures, a significant wave height and surge depth, since these are the parameters that we need to evaluate this function. And the structural parameters as well, based on the group H, following the paper, based on group 4, because the structure was constructed after the year 2000, and the height of the lowest horizontal member, that is actually how the height of the elevation of the house. We define this using a log normal distribution, since it's, since the results are so sensitive to this factor. To incorporate degradation in the model, we use a reduction factor R that is expressed as a percentage of the existing fragility or the existing vulnerability of the system. So what we do is the probability of failure that we calculate from the fragility function, we multiply it by this factor. For the year 2050, we defined this factor of degradation on 25%. For the loss model, we first calculate the building replacement value, where the replacement value of the structure is calculated based on RS means data. We multiply by an allocation factor given for the Galveston Island. So we compute the loss by the probability of failure, multiplied by the factor between the cost and this factor here that will tell us how much it will devaluate over time. This set as 3%, that is the discount value, and T represents the service life of the structure, in this case 30 years between 2020 and 2050. Here we can see the results of the experience probability of the loss, given that a hurricane with the characteristics analyzed occurs in the year 2050 for 2 cases. The first case, no evidence, and the second case, we have evidence that the representative concentration path is 8.5, and we set the height of the structure as the mean value, that is 15 feet. So what we can see is that when we include evidence, the uncertainty in the losses reduces significantly. So for example, if we set a value of experience probability of 5%, we can see that in the case of evidence, we get an approximate value of $19,000. That is approximately 4% of the total cost of the house. But if in the case of no evidence, we have a value of approximately $30,000 that corresponds to 7% of the cost of the structure. Some summary and conclusions of the work. Performance-based coastal engineering framework was proposed for design campus assessment of coastal structures, considering time-varying factors. The proposed framework is implemented using Bayesian networks, forming causal dependencies among certain parameters that we can form according to engineering judgment. And then a case study of an elevated residential coastal structure subjected to surge and wave loads is presented to showcase the efficacy of the framework and evaluate the uncertainty of the decision variable, that in this case was the losses. Some contributions of the work include the incorporation of time-varying factors in a performance-based framework, the incorporation of Bayesian network representation of performance-based frameworks, and we showcase the capability of probabilistic inference from observed evidence using Bayesian networks. Finally, I would like to finish with the acknowledgement, the financial support of the National Science Foundation under the PIRE program and Rice University. With that, I finish. So thank you very much for your attention.